Assalamualaikum and good afternoon.
Akak dah masuk. Akak dah masuk sini kan? Yang share screen. Akak dah share audio dan video kan? Ada kan? Akak ingatkan dalam grup tak? Akak ingatkan lah. Akak cakap please enter the parallel session. We will start at the don't forget to share video and audio kat jangan lupa cakap. So kita ada berapa orang nanti Ada 1, 2, 3, 4, 5, 6, 7, 8, 9 orang. Dia tak? 9. Oh ada 8 orang. Dia tak audio. Tak.
Bismillahirrahmanirrahim. Assalamualaikum and very good afternoon. Ladies and gentlemen, we are about to begin session C entitled Biomaterials Polymer 2. Please stand by. I would like to seek for your kind cooperation to avoid any virtual disturbance during the live broadcast session. If you have any question, the conference resource personnel are ready to attend you at the reception desk. Thank you for your kind cooperation and attention. We will start at 3:40 p.m., which is approximately 5 minutes from now.
So Dr. Mukhalid will start.
Yeah. Yeah. Now we are waiting. Just you are ready. Now can start. So,
Okay.
okay. Bismillahirrahmanirrahim. Assalamu alaikum and very good afternoon, ladies and gentlemen. I would like to take the opportunity to welcome you all here today at the first Malaysia International Conference on Nanotechnology and Catalysis 2021. We are now in session C entitled Biomaterials Polymer 2. My name is M.A. Mutalif Hussain and I am a postdoctoral research fellow at Nanotechnology and Catalysis Research Center, University of Malaya. I will be the session chair today, together with the session moderator, Madam Suzaimi Johari and Miss Leah Jaharani. I invite all the invited speakers and presenters to request to share audio and video now. Before getting started, I would like to share some announcement. Ladies and gentlemen, oral presentations will be evaluated for the awards under two categories. Number one, best session presenter that will receive the certificate for the best presenter, and I will announce at the end of this session. Best Presenter Award that offered prize money from 500 to 1000 Malaysian ringgit, trophy and award certificate. This will be announced during the closing ceremony. I would like to seek your kind cooperation to mute your microphone if you are not presenting and avoid any virtual disturbance as possible. For those who intend to ask the question to the presenter, you can channel your question in the QA box. I will read it after every presentation. You can also request to share your audio and visual to ask you question in live mode. Presenters are given 15 minutes for presentation and 5 minutes for Q&A session. Whereas invited speakers are given 25 minutes for presentation and 5 minutes Q&A. I will remind the presenter to end of the presentation 2 minutes before the presentation session ends. I will stop the presentation session when the session has exceeded the 5 minutes allowed. Before we started this parallel session, I would appreciate if everybody can turn on camera for a photo session. Our moderator and IT personnel will take the screenshot. I would like to request all our participants to on the camera. Is it okay? Miss Leah? Okay. Thank you all for your kind cooperation. Now we are moving to our presentation session. without further delay, without further delay, we will have a presentation from Mr. Tornekson Dolkun entitled Rubber Kinaf-based nanocellulose reinforced green materials with their toxicity. Please welcome Mr. Dolkun. The floor is yours. Sorry, sound. We are not hearing the sound. Excuse me, we are still not hearing the sound. Can you please, our IT personnel can help to improve the sound of these videos.
Did you hear the sound? Sorry?
Yeah, excuse me. Yeah, we are hearing from you, but not from you.
Okay.
Excuse me, from our previous experience, if you have the microphone from your own, sometime videos is playing without sound. Maybe you can remove microphone, then can try.
Sorry for the technical problem. Can we proceed with the next presenter, Miss Anusha, while we are fixing our technical problem? So sorry for the inconvenience.
Okay. We are extremely sorry for technical problem. We have to move our next presenter. Our next presenter is Miss Anusha Ashuhan. She will speak on preparation and characterization of cellulose, nanocrystal, alginate, propylene glycol, diacrylate as bioink paste for bioprinting application. Please welcome Ms. Anusha Ashuhan. The floor is yours.
Hi, good evening. Thank you very much. So I will share my screen. Oh, I cannot share my screen. I've clicked share, but it does not appear.
Excuse me, it is not accessible, or
I can choose what to share, but when I click the share button, it does not appear.
Excuse me, our IT team can please help Miss Anusha. Any problem for sharing?
Can you please send your files to WhatsApp? Yeah.
Okay.
Yeah.
We are still sorry for our technical problem. Please wait. We like to request your patience for our delay. Ladies and gentlemen, we appreciate your patience. Our IT team and doing to solve the technical problem. We apologize in inconvenience. Miss Anusha, I would like to request you to, can you please refresh your browser and can try again?
Oh, okay, let me try.
Okay, please kindly.
All right.
Refresh your browser and can try again, please.
I still cannot share it.
Thank you. Oh. Yes, now okay.
Okay, so I will start now.
Okay.
Okay.
Thank you. You can start.
Good evening to the panel and the participants present here today. My name is Anusha, and today I'll be sharing about my project involving the formulation of bioinks for bioprinting application. So the next slide. "3D bioprinting may not be a familiar topic to some of us because it's a rather recent technology. The idea of printing tissues and organs sounds like science fiction, right? Well, not anymore. It is possible to print out human tissues and organs, but of course, it's not as easy as it sounds. There is a lot of research and experiments required before we move them to the clinical stage." Next slide. Some of the main goals of 3D bioprinting includes solving the issue of organ transplant shortage, A patient often have to wait many, many years before they get a transplant. And when they do get the transplant, there is the risk of rejection due to the immune response. With bioprinting, we will be using the patient's own cells, which eliminates this risk of rejection. Another goal of bioprinting is the regeneration of damaged bones and tissues, which is the objective of my project that I'll be touching more about later. And the other important application is also to improve drug testing to eliminate the need for animal testing. We hope that with 3D bioprinting, it will offer a more sustainable and effective approach without animal testing. Next slide. So for this study, we mainly focus on the application of bioink in the regeneration of articular cartilage. I'm sure one of us have sometime or another heard someone we know complain about their knee pain, right? And climbing up the stairs, running or jumping. Maybe we've experienced it ourselves. Osteoarthritis is actually a very common problem that affects many people. And the articular cartilage can be easily damaged from overuse, injury, or as a natural aging process. And unlike bones, they have limited capacity for self-repair because of the absence of blood vessels, therefore making efforts for treatment challenging. With 3D bioprinting, we hope that we will be able to regenerate the articular cartilage to its native fully functional form. Next slide. And the success of 3D bioprinting begins with the biomaterials. So the basic requirements that the ideal bioink should satisfy is number 1, the printability, number 2, mechanical properties, and number 3, the biocompatibility. The biomaterials chosen should be suitable for its intended application. So for this study, the biomaterials chosen is suitable for articular cartilage applications. Next slide. In this study, we have chosen 3 biomaterials that will be used for cartilage applications. The first biomaterial is CNC. CNC is sourced from cellulose, which is the most abundant renewable source available today. And the reason why CNCs is preferred over CNF or other types of nanocellulose is due to its high crystallinity. It gives it its high tensile strength and elastic modulus, which make it highly favorable as a reinforcing material, especially for bioink applications. CNCs are also widely used in tissue engineering because of its ability to adhere to cells and encourage cell growth. And the second biomaterial is alginate. Alginate has unique solid gel state, which allows the formation of a hydronal network using the cross-linking by calcium ions. And the fast gelation rate that alginate has also makes it suitable for extrusion bioprinting. Alginate is also widely used as a biomedical product because of its low toxicity and good biocompatibility. And the third biomaterial is PEGDA. PEGDA has been approved by the FDA and has shown to have little to no immunogenicity. Therefore, it is less likely to provoke an immune response, which is important in bioprinting applications. And the advantage of using PEGDA is that we are able to tune the properties, which means we can use different molecular weight of the PEGDA, also use different concentrations, and control the UV exposure to match the properties that we would like. PEGDA is also have good mechanical properties that is suitable for the cartilage. Next slide. So from these 3 biomaterials, which is a mixture of both natural and synthetic polymers, we introduced a double network system, which will help to improve the mechanical properties of the hydrogel. So this double network bioink is formed from 2 cross-linking mechanisms. Number 1 is the physical bonds by calcium ion interaction, and the secondary cross-linking by UV. So in this study, we attempt to formulate a bioink that will satisfy the properties of the cartilage. Next slide. This is the flow of the methodology carried out during the project. So the first part is the extraction of CNCs, followed by formulation of bioinks, mechanical properties testing, rheology analysis, and finally swelling behavior observation. So next slide. The first part is the CNC extraction. After grinding the oil palm trunk fibers, they were then extracted using the Soxhlet extraction method, followed by delignification via bleaching. After that, the hemicellulose region is removed using potassium hydroxide, followed by acid hydrolysis, which will further process the fiber to obtain the crystalline region. And after rinsing with distilled water, they are subjected to dialysis, followed by sonification, homogenization, and finally they are freeze-dried. Next slide. For the second part is the bioink formulations. So 9 different formulations with different concentrations were prepared. They were prepared separately and then they were mixed together to form a homogeneous pre-gel bioink. And later they are added with the cross-linking agents, which is the calcium sulfate and the photoinitiator, to form a gel bioink. Now this gel bioink is then loaded into the syringe and the constructs are then extruded based on the desired shapes that we choose. And after it is extruded, we then subject it to UV light under 365 nanometer wavelength. Next slide. The next part is once we have the hydrogen constructs, we tested their mechanical properties using the manual compression. So they are compressed manually, and then the condition of the constructs before and after are observed to see how they respond. For next slide. The fourth part is the rheology analysis. So rheology analysis is important in bioprinting because it gives us an idea of how the bioink will respond and to see if it's actually suitable for extrusion bioprinting. There were 2 parameters that we tested. First is the shear thinning behavior. Second is the storage and loss modulus. And this is tested with the Anton par rheometer. And the next slide is the swelling behavior observation. The dry weight and the swollen weight of the hydrogels were recorded, and then they were used to calculate the water content and the mass swelling ratio using these equations. Next slide. Now we move on to the results and discussion. Figure 4 shows the end product of the CNC powder form that is ready to use. So the production efficiency of this extracted CNC is about 33.75%, which is within the range of expected efficiency when we are using high sulfuric acid concentration. When strong acid is used, the yield is usually lower because the content is purer. This is because the sulfuric acid will attack the amorphous region of the fiber, leaving only the pure crystalline region. And this method is still the most commonly used treatment today, even though that the yield is lower compared to other treatment options. Next slide. This is the TM image of the extracted CNCs. They exhibit typical rod-like structures, and the geometric distributions and the size of the CNCs, they differ based on the method of preparation as well as the source of the fiber. Here, the extracted CNCs have an average length and diameter of 145 nanometer and 7.7 nanometer respectively. Next slide. Now we go to the bioink formulations. So for pre-gel bioink is the picture on the left. It's in liquid form, and at this state, they are unable to form any constructs because of the very low viscosity. Upon addition of the calcium sulfate, which is the picture on the right, they form gel, and then they can form simple constructs. At this state, they are single network bioinks. So although they are able to form simple constructs, they are still not stable because when the height of the constructs increase, they will still collapse, or when force is applied, they will also collapse. Next slide. And then when they are subsequently UV cross-linked, they become firm and stable. At this rate, they are double network bioinks. So you can actually pick this up and then they will not be destroyed as compared to the single network bioinks. And an interesting observation is that the bioinks with CNC show the appearance of like flexible, spongy, elastic-like texture compared compared to the formulations without CNC, which shows hard and brittle characteristics. This result suggests that the addition of CNC actually improved the appearance of the hydrogel, making them have a closer resemblance to the soft native tissue. Next slide. This shows the addition. Yeah, this is the manual compression of the. Yeah, play this video, you can watch. When the load is compressed, the hydrogel is compressed, and then once the load is lifted, it is able to return back to its original shape. And this shows that the construct is load-bearing, which is what we want in the bioink for cartilage printing applications. Sorry, there are a few animations here. Thank you. Oh, sorry. Okay, so from the study done by Tang and colleagues, they actually reported that the nanocellulose content influences the stiffness and elasticity of the hydrogel construct, which means that we can actually play around with the CNC concentration to make it match the compressive modulus of the native articular cartilage. So this will be good for future studies if we want to do further study. Next slide. The next part is the rheology analysis. First, we look at the shear thinning behavior. Figure 1 shows the flow curves of the different formulations using low alginate concentration at 1%. So the formulations with CNC, they show pronounced shear thinning behavior, which is the formulations with CNC are the ones in red, the red flow curves, while the formulations without CNC are the formulations without, the black flow curves are the formulations without CNC. So the formulations without CNC, which is the black flow curves, show that they have minimal to shear thinning behavior. And when CNC is added, it actually improves the shear thinning behavior. So shear thinning behavior is important because it influences the printability of the bioink. Next slide. In figure 2, the flow curves show the other 5 formulations at higher alginate concentrations. So at higher alginate concentrations, there is still shear thinning property, but it is not as pronounced as the shear thinning behavior at low alginate concentration. This may be because of the ratio and concentration of CNC and alginate. At higher alginate concentrations, another one more click. Yeah, the properties of alginate may have overshadowed or become dominant over the CNC. That is why the shear thinning behavior is also reduced at higher alginate concentrations. Next slide. And the next part, the second rheology analysis, is the storage and loss modulus. So for the storage modulus is the square symbols, while the loss modulus is the triangle symbols. We can see that throughout the whole frequency range, the storage modulus is higher than the loss modulus. So this indicates that the gel have a stable internal structure and have good print fidelity. Print fidelity is important because it helps to, we want the construct, the printer construct, to be as close or as accurate as possible as to the construct that we design. And the data will show that the bioink formulations with CNC, which is the orange, the blue, and the red one, they have higher storage and loss modulus values compared to the bioink formulations without CNC, which is the black flow curve. This shows that the addition of CNC does have a positive effect on the print fidelity. Next slide. Here from the data is the swelling behavior. We see that as alginate and PHDA increases, the equilibrium water content and swelling ratio reduces. This is because of the increased cross-linking reaction that makes the uptake of the water reduce. For formulation 8, you can click the slide. We have the water content of 79.5%. And at 79.5%, it's actually within the range of the articular cartilage. And this is good because we want the scaffold to resemble as close as possible to the actual tissue environment. so that the regeneration is better and the cells can be able to form their own extracellular matrix easier. Next slide. So in conclusion, first we were able to formulate a double network bioink using CNC, Alginate, and PHDA. And second, based on the preliminary results, it is suggested that the F8 formulation shows good potential for cartilage printing application, so it can serve as a guide for future studies if you want to optimize this bioink. Third, so this project is still very early in its progress, still needs a lot of further tests, so we should conduct further tests like FDR analysis, cell viability tests, and degradability tests to solidify its application in bioprinting. And lastly, these findings of this study will be definitely beneficial to patients who are suffering from osteoarthritis, because 3D bioprinting can offer a better treatment option as a long-term remedy. Yeah, that is all from me. Thank you very much.
Thank you, Ms. Anusha, for your interesting topics
Thank you.
sharing with us. Now we are moving to Q&A session. There is still no any question from QA box. I would like to give opportunity for all the participants can on the audios and can ask any question.
I think from the chat box there is a question from Miss Lee.
Yeah. In
CNC, yeah. It can disperse well because it's used the sulfuric acid, so there is sulfate groups present in the CNC. So it does disperse, but then if you leave it over time, it will actually sink to the bottom. So what we do is we combine these three biomaterials together, CNC, PGDA, and Alginate. And then once we added the calcium sulfate, it becomes homogeneous, and then the distribution is better. Yeah, it becomes locked. I hope that answers your question.
Okay, thank you. As no more question, I would like to ask one question. How you optimize the CNC, Alginate, and PEGDA? What was your optimized percentage of these three components of your bioink?
Sorry, I don't. Can you repeat again?
Just I would like to know, how do you optimize your three components? One is the CNC, Alginate, and polyethylene glycol diacrylate. What was the optimization condition, and how percentage of the optimization condition, and how did you optimize this one? This percentage is okay or not? How you confirm this?
For each of the biomaterials, I actually tested out the lowest concentration. So the lowest is 1% alginate, and then all at lowest, and then the highest value. Because before this study, I also conducted a preliminary study that sees which one is the better and the. So at higher concentration, once they were able to form their own structure, we then subjected them to the test that I mentioned earlier. So based on the so from the formulation, so you mean this part, right? Yeah. So we tested out different at different low level and high level, and then once we test out every single optimization, then we were able to find out which of the concentration is the one that gives the better mechanical properties. Because for this study, we only tested out for the mechanical properties, so that was the only variable that we tested.
Thank you. Thank you. As still no have any question, so we are moving to our next presenter, Mr. Dolkun. He will present about the rubber kinase-based nanocellulose reinforce green materials with their toxicity. Please welcome Mr. Dolkun. The stage is yours.
Tak boleh. Okay.
Excuse me, our IT team, may you assist us? We are still waiting.
Is there toxicity? The contents of my presentation including introduction, objectives, methodology, result discussion, as well as conclusion. The isolation of polymer from renewable biomass resources has attracted much attention among researchers. Among various biorenewable polymer, cellulose is the most abundant and the fascinating natural organic polymer on the Earth. It was discovered 2 centuries ago, but recently more and more research focus on cellulose. Due to its lightweight features, mechanical and chemical properties, biocompatibility, low toxicity, while being a renewable material that has the potential to revolutionize the future with relatively low production costs. Unlike some synthetic polymers, these features allow the diverse application on cellulose in the production of materials that are environmentally friendly and safe to humans. The main type of nanocellulose including nanofibrillated cellulose, nanocrystalline cellulose, and bacterial cellulose. In this study, we're focusing on the nanofibrillated cellulose and the nanocrystalline cellulose. In the picture, we can see A is nanofibrillated cellulose, and B is nanocrystalline cellulose. The main difference is about the amorphous region. Nanocrystalline cellulose has both amorphous and highly ordered crystalline cellulose structure. NCC not only keep its performance but also manifests all the overwhelming advantages through its dimensions. The objectives of the study to determine the capability of production waste fiber to produce nanocrystalline cellulose, nanofibrillated cellulose from different biomass. To compare the quality of nanocrystalline cellulose and nanofibrillated cellulose synthesis from the rubber raw biomass and the canal-based raw biomass. To evaluate the cytotoxicity of the synthesis nanocellulose using the morphologies raw 264.7 and the HACAT cell line to determine effects of disease cell model and a healthy cell model, respectively. The reason why we used HACAT cell is due to their potential application as antiseptic gels or bioactive masks, which is our ongoing project related to skin cells. Methodology. Above all, I want to talk about the materials. The raw rubber wood biomass and the raw canal-based biomass obtained from local company is agriculture biomass. All chemicals were analytical grades and used without the further purification. The main methodology including two steps. One is synthesis of nanocrystalline cellulose, another one is synthesis of nanofibrillated cellulose. The two-step little bit differences. For synthesis of nanocrystalline cellulose, need pre-treatment from fiber cell walls is extracted cellulose. After that, we're using sulfuric acid for hydrolysis process. For nanofibrillated cellulose, first of all, delignification lead to remove the lignin content of the cellulose raw biomass. Later on, we're using hemicellulose removal. After that, we're using mechanical treatment, milling the extracted cellulose. We're also using toxicology assessment, cell viability, and nitric oxide assay. In the end, we're using nanocellulose prepared reinforced polymer matrix. Synthesis of nanocrystalline cellulose. The first step is alkaline treatment. Then we bleaching with different parameters. We're using freeze drying for our drying process and acid hydrolysis. After acid hydrolysis, we repeated step 3, drying process. For synthesis of nanofibrillated cellulose from raw biomass, rubber wood biomass, and canal-based biomass. Above all, hemicellulose removal and delignification. Mechanical treatment. After mechanical treatment, we're still repeating the step drying process, still using freeze dryer. Then we're able to collect nanofibrillated cellulose. And finally, we use a mechanical performance for tensile testing. We're using complete and medium for 24 hours respectively. The reason why we use HACAT cells is due to their potential application in anticipates gels or bioactive masks with its or ongoing project related skin cells, whereas raw 264.7 morphologies are among the most important cellular components of innate immunity, and they are considered to have higher capacity to internalize nanomaterials more efficiently than any other cellular types in the body. For FESEM, we checked overall morphology of the raw biomass, kanaf, and the rubber wood. After that, multi-step chemical purification, we get extracted cellulose. Clearly, the size is decreased dimension. For nanocrystalline cellulose, we're using different methods, different parameters. When acid concentration is same as 48%, we're using different reaction time. When reaction time is 45 minutes, we get smaller dimension compared to extracted cellulose. But when we increase the reaction time to 120 minutes, is 2 hours, we get even smaller size. I can say it's perfect nano size. For nanofibrillated cellulose, clearly give little bit high dimension compared to nanocrystalline cellulose, according to the FESEM images. For determining the dimension, we're using TEM analysis. Nanocrystalline cellulose and the nanofibrillated cellulose both giving the similar morphology, needle shape, but nanocrystalline cellulose giving the much smaller size dimension. Both of them have similar diameter. For nanocrystalline cellulose around the 5 nanometer, 5.2. For nanofibrillated cellulose 5.8, almost same, but their length is different. It's big differences. For nanocrystalline cellulose, the length is around the 30 to 35 nanometers, but for nanofibrillated cellulose, it's existing 100 nanometer. The average length is 169 nanometers in our study. Compared to different nanocrystalline cellulose according to their researchers, one is rubber wood and one is kanaf. Nevertheless, kanaf-based nanocrystalline cellulose shows uniform size distribution with the highest frequency in the smaller dimension. Nanofibrillary cellulose with wide heterogeneous distribution both in width and in length. We run FTIR from the raw nanocrystalline cellulose for both kanaf-based and rubber-based. After that, we're using multi-step chemical and mechanical performance, getting the extracted cellulose and nanocrystalline cellulose, nanofibrillated cellulose. We run again the FTIR for comparison. Compared to the raw biomass, extracted cellulose clearly lose some peaks. After that, nanocrystalline cellulose. We clearly see OH strength from 3000 to 3060 became decreased. And 1750 for lignin and 1250 for hemicellulose also disappeared from the FTIR peaks. It shows we successfully removed the lignin and hemicellulose from the raw biomass and getting the pure cellulose. We run in the XRD analysis for checking the crystallinity. For raw biomass, giving nearly 60. After extracted cellulose giving little bit highest crystallinity. The much highest crystallinity from the nanocrystalline cellulose, which almost exists 60, 70. Compared with nanocrystalline cellulose and the nanofibrillated cellulose, nanocrystalline cellulose giving little bit higher crystallinity than nanofibrillated cellulose. TGA analysis. Depend on the reduced weight percentage in the TGA analysis, both rubber and the kanaf-based nanocrystalline cellulose mass weight were 32.5 and 48.5 respectively. The amount of residue from the nanocrystalline cellulose is higher than extracted cellulose in the raw samples due to the high purity than other samples, which did not include non-cellulosic content and ash. The polymer decomposition area of nanocrystalline cellulose showed the highest thermal stability than other samples. It means that it has many potential applications in composite materials. TGA analysis for nanofibrillated cellulose. For nanofibrillated cellulose from kanaf giving 27.3 mesh weight as reduced weight percentages residue. Cytotoxicity testing analysis. The toxicological effects of nanocellulose on human, animal, and the environmental are largely unknown, especially hazards in the identification of daily risk from the occupational exposure. Since nanoparticles have a considerable potential for industrial application, additional work is necessary to obtain further information on their toxicological characteristics and their possible impacts on human health and safety. Most studies showed nanocrystalline cellulose and the nanofibrillated cellulose to have negligible cytotoxicity effect, but the various types of cellulose biomass sources and the synthesis process of nanocellulose may affect the cell viability. In the study, Rho 264.7 and HSCA cells were exposed to different nanocrystalline and nanofibrillated cellulose concentration for 24 hours, and cell viability was analyzed using the MTT assay. The percentage of cell viability in the medium was mainly dose-dependent. The viability of morphogenous cells was not affected when exposure to enough nanocrystalline cellulose at concentration of 300 to 1000. While the viability of the morphogenous improved when exposure to rubber nanocrystalline cellulose, at concentration of 300 to 1000. From source-based study, reconformant knaphead-based nanocrystalline cellulose demonstrated better cytotoxicity than rubber wood-based nanocrystalline cellulose. Thus, we selected knaphead as a source for further size-based study that same resources but different type of nanocellulose. For nanofibrillated cellulose, we're choosing knaphead-based raw biomass for synthesis processing. Mechanical performance of reinforced nanocellulose reinforced polypropylene polyethylene matrix by wet spinning, and nanocellulose reinforced PEO matrix by electrospinning. Reinforced PEO matrix prepared by electrospinning. When we add some limited nanocrystalline cellulose to pure PEO, we clearly see the tensile strength increased. When we add to nanofibrillated cellulose to pure PEO, we see the differences, which is nanofibrillated cellulose giving better performance than nanocrystalline cellulose reinforced PEO. In other two samples giving the same. When we add nanocrystalline cellulose to the polypropylene, and the nanofibrillated cellulose to polypropylene, nanofibrillated cellulose giving the highest tensile strength than nanocrystalline cellulose polypropylene matrix. For polyethylene is the same. NFC gives highest performance than NCC. The conclusion: the main goal of the present work is to study the physiochemical properties of the nanocrystalline cellulose and nanofibrillated cellulose using two different sources of fiber, namely raw rubberwood biomass and raw knaphead-based biomass. Compare their qualities and evaluate the cytotoxicity of the nanocellulose as synthesis. The future study, nanocellulose reinforced materials can be applied as an enhanced tire for truck or other vehicles, or helmet for self-protection products, 3D printing, as well as medical implants. Nanocellulose-based biomaterials can be further utilized in medical implants, such as molecular cartilage, and bone implants. Thank you.
Thank you, Mr. Dolkon, for sharing interesting topics. As Mr. Dolkon is not in live, so we have to escape Q&A session, and we are now moving to invited speech session. The first invited speaker in this session is Dr. Noor Hidayatul Laili Muhammad Zulkifli, Senior Lecturer, Nanotechnology and Catalysis Research Center, University of Malaya. She will be talking about light sensitivity modification of titanium dioxide photocatalyst by Kitusan biopolymer for decomposition of synthetic dyes compounds. I would like to welcome Dr. Noor Hidayatul Laili Muhammad Zulkifli. The floor is yours.
Thank you to the chairman, Dr. Mutalib Hussein, and thank you for everyone to stay until my presentation. To start the presentation, I would like to ask assistance from the IT community to share my pre-recorded video. Hi everyone, I'm Dr. Laili from University Malaya. Today's presentation, I will focus on how we're going to utilize natural energy in this context is sunlight to mitigate or degrade the persistent pollutants from the industries in order not only to generate a sustainable ecosystem, but also give a positive impact on the environment, humanity, and socials. The title of today's presentation is the titanium oxide, zinc oxide supported chitosan, photocatalysis to the absorption and photodegradation process of the synthetic dye. And together with me to develop this project is Mr. Azam and also Prof. Rafi. So enjoy the presentations. Wastewater from the dye is the huge pollutant around the world. Some dye doesn't even degrade in water. Others that do degrade produce the harmful substance as they are decomposed. Additives used during the dye process include the harmful substance, including acid and alkalis. The question here is, are the synthetic dye harmful to environments? Synthetic dye have the harmful effects on the environments and human beings. Exposed to the large doses of this substance can be toxic and can have several effects in the human bodies. Water pollutants can also result from the manufacturing synthetic dye when the untreated dye is dumped directly on the bodies of water. In conjunction of the 2018 edition of the United Nations World Water Development Report, stated that nearly 8 billion people will suffer from the clean water by 2050. This is the result of increasing demand of water, reduction of the water resources, and increasing pollutant of water, driven by the dramatic populations and the economic growth. Conventional approaches, including biological, chemical, physical methods, have not been achieved the complete degradation of the organic pollutants. Besides, it also requires a long operation times and procedure secondary, and it have a possibility to produce a secondary pollutants, which is increase the cost of the process. Since its emergence, the advanced oxidation process, or we know as the AOPs, have gained a great deal of interest in the wastewater treatments and recycling technologies. Relative to the traditional methods, these AOP are efficient in treating the wastewater to degrade a wide variety of the organic pollutants. The problem faced by the treatment of processes as sludge developments, the formation of the secondary contaminants, high cost, and the incomplete degradation of the organic pollutants render the AOP more effective technologies. Photocatalysis process belong to the advanced oxidation technology for removal of the persistent organic pollutants and the microorganism from water. The photocatalysis is a process in which the light energy is used to derive the pair of the chemical reactions. Due to their activated stage, the electron in the hole perform chemical reductions and the oxidation as through they were highly reactive reagents in the chemical reactions. Photocatalysis process belong to the advanced oxidation technology for removal of the persistent organic pollutants and the microorganism from water. The photocatalysis is a process in which the light energy is used to derive the pair of the chemical reactions. Due to their activated stage, the electron in the hole perform chemical reductions and the oxidation as through they were highly reactive reagents in the chemical reactions. Several numbers of the metal oxide catalysts, just as the titanium oxide, zinc oxide, or strontium oxide, have been applied or tried for the photocatalytic water degradations. Among these catalysts, titanium oxide have been demonstrated to be an excellent catalyst in photodegradation of the organic pollutants due to the effective, non-toxic, low-cost, photostable, cost-effective functional materials and can be reused. It means that we can recycle it. Titanium oxide generally is considered as the best photocatalyst and could detoxification water from the several organic pollutants. In addition, titanium oxide have the large surface area that can facilitate the fast rate of the surface reactions, which has attained considerable attentions due to its distinctive application as the photocatalyst. However, there are still limitations of the titanium oxide as a catalyst, and is still far from becoming a potential candidate in the environmental treatments, water treatments. The efficient use of the visible light from our sunlight and improvement of the photocatalytic activities are the two important issues must be addressed to make the economical viable on the large-scale environmental remediations. Therefore, the high photocatalytic activities of the titanium oxide photocatalyst could be achieved with the suitable architecture that minimize the recommendation of the photo-induced electron hole pair by quickly separate them before the electron hole pair lost their energy in the form of the heat and photon through the recombination process. Furthermore, the titanium oxide could not use satisfactorily due to its poor separation ability from the suspensions and flowability. Titanium nanoparticle-based photocatalysts have demonstrated a promising dye photodegradation efficiency up to 95 to 97% under the UV irradiations. In order to enhance its light sensitivity under the solar irradiations, coupled with the zinc oxide has been proposed here. Zinc oxide is a promising semiconductor photocatalyst on the account of its wide band gap. Is it 3.7 eV, low cost, non-toxicity, and a good oxidizing power. On the other hand, electron hole recommendation is the major impedance to the widespread application of its photocatalytic activities. Compared to the titanium oxide, zinc oxide can absorb a large portion of the UV spectrum and show a superior photocatalytic properties. However, the photocatalytic capabilities of the zinc oxide are limited by the wavelength of the UV light, and it cannot absorb the wavelength of the UV light. Some problems remain to be resolved in its application, just as the rapid recombination of the photogenerated electron hole pair, and improving the photocatalytic activity of the zinc oxide has therefore become a hot topic for researchers in the recent years. One approach is to combine zinc oxide with other materials to form a hybrid photocatalytic system, thereby can improve the separation of the photogenerated electron hole pair. Zinc oxide is a promising semiconductor photocatalyst on the account of its wide band gap. Is it 3.7 eV, low cost, non-toxicity, and a good oxidizing power. On the other hand, electron hole recommendation is the major impedance to the widespread application of photocatalytic activities. Compared to the titanium oxide, zinc oxide can absorb a large portion of the UV spectrum and show a superior photocatalytic properties. However, the photocatalytic capabilities of the zinc oxide are limited by the wavelength of the UV light, and it cannot absorb the wavelength of the UV light. Some problems remain to be resolved in its application, just as the rapid recommendation of the photogenerated electron hole pair, and improving the photoconductivity of the zinc oxide has therefore become a hot topic for researchers in the recent year. One approach is to combine zinc oxide with other materials to form a hybrid photocatalytic system, thereby can improve the separation of the photogenerated electron hole pair. To solve this problem, chitosan-based particle composite have been studied increasingly as an alternative adsorbent in the water treatments, just as using the metals, metal oxide, and bimetallics. Furthermore, chitosan can act as the coagulating or floculating agents to remove several types of pollutants, including organic compounds, metal, and other from the contaminated water. It also been already used in the organic matter removal for the wastewater, especially those resulting from the food processings, being very effective in reducing the oxygen chemical demands. It is well known that application of the photocatalyst, just as from the metal oxide, titanium oxide, and zinc oxide, is limited by the actual facts that UV activation is required. The blanket energy is about 3.2 UV, and this implies that lower than 5% of the solar spectrum has sufficient energy to activate the photocatalyst, and by the fast recommendation rates of the electron hole pair generated. Hence, modification of the photocatalyst through the metal or non-metal doping of their recombination or with the other semiconductors are the common methods used to improve the photocatalytic performance and for the activation by the visible light irradiations. Therefore, zinc oxide was combined here to endow the titanium oxide nanoparticle with enhanced absorptions of the visible radiations, thus can improve its photocatalytic activities. It's also been reported that the heterogeneous photocatalytic reactions will be performed at the surface rather than the solution box, and the surface properties of the titanium oxide are critical for the efficiency. Per absorption on the surface of the titanium oxide particle is required for the efficient photocatalytic regulation of the dye, and more significant absorption enhance the rates. This approach target the use of the supported materials, such as microporous solvite, zeolite, mordenite, activated carbon, alumina, silica, microporous silica on the surface. Hence, most of the photocatalytic activities were enhanced in these contents. And here, chitosan is used as a support material due to the presence of the amino and hydroxy group, which serve as the active site capable for enhancing the absorption properties of the hybrid catalyst. The particle size, morphology, nanoscale photocatalysts are also a problem in the full-scale water and wastewater treatment because the particle should be removed or recovered after the treatments. To address this problem, chitosan-based particle composite have been produced in the microbits, which can be filtered out by the simple filtering process at the end of the treatments. The immobilization of the catalyst has brought increasing the interest to the study of the polymer-based composite, whose porosity and the pore size can be controlled. These research provide a simple and readily accessible route to the formation of the ternary titanium oxide, zinc oxide, and chitosan, which overcome the charge recommendations and separation limitations of the native titanium oxides. The modification allowed the titanium oxide to be a photocatalytic under the visible light sources. And chitosan is sensitive to the various types of the photooxidation of the UV light. The chemical structure of the chitosan change due to the cleavage of the glycosidic bonds and the formation of the new carbonic groups in the chitosan oligomers. When a colored organic compound is present, it acts as the photosynthesizer and have a capability of injections and electrons into the conduction bands of the semiconductor particles to generate an oxidation process. The oxidized form of the dye molecule is further degrades. Through a simple mixing method, these ternary systems can be produced by the Catalysis process and have relatively high absorption capacities, but once water treatment is treated, the catalyst can be reused effectively. This methodology has provided more sustainable treatment process than the other approach. To solve this problem, chitosan-based particle composite have been studied increasingly as an alternative adsorbent in the water treatments, just as using the metals, metal oxide, and bimetallics. Furthermore, chitosan can act as the coagulating or floculating agents to remove several types of pollutants, including organic compounds, metal, and other from the contaminated water. It also been already used in the organic matter removal for the wastewater, especially those resulting from the food processing, being very effective in reducing the oxygen chemical demands. The hybrid system have been performed using the simple acetate process with the acetic acid as the medium. Then the obtained photocatalysis has been characterized in terms of its surface and the structural properties. Before it been proceed with the photocatalytic analysis under the visible regions using the methylene blue as the model of synthetic dye pollutants. The surface morphology analysis of the hybrid catalyst was performed to investigate the dispersions of the zinc oxide and titanium oxide over the supported chitosan with the field immersion scanning electron microscope (FEM). The image demonstrates that not spherical shapes but with the macroporosity structure has been observed. The porous structure is attributed due to the presence of the chitosan macromolecule, which can be further assessed as the absorption site during the dye treatment. Characterizations using the Fourier transform infrared F-type spectroscopy analysis provide information regarding the active surface and the functional group of these hybrid systems. The FTR spectrum of the chitosan exhibit the absorption bands at 3447 and 1651, which is attributed to the primary amine and hydroxyl functional groups. The FTS spectrum of titanium oxide exhibit a broad absorption bands at 3441, which confirm the OH stretching vibration of the adsorbed water on the TiO2 surface. The peak at 499 show the distinct stretching vibration of the TiO2. The band of the TiO2 chitosans means that the connection band of the TiO2 and chitosan reveal the anti-gold characteristics for both chitosan and titanium oxides. The strong peak at 3441 is shifted to the lower wavelength, which correspond to the stretching vibration of the hydroxyl and the primary amine group, and become border indicate some interactions between this group and the titanium oxide. The peak at range of 1000 to 1600 are ascribed as the bending vibration of the primary amines and stretching of the carbonic groups. The intensity of this peak in the titanium and chitosan has been attributed to the less available of the free hydroxyl and primary amine group of chitosans and their respective involvements in the bonding with the TiO2. And these groups serve to coordinate and reaction site for the absorption of the organic compounds. Furthermore, the peak at the 400 to 900 refer to the OTiO2 bonds that prove the combination of the TiO2 and the chitosan matrix. Therefore, the stretching vibration of the hydroxyls and the primary attract the involvement of the functional group present on the surface of the TiO2 and chitosans during the methyl blue absorption process. In order to examine or to demonstrate the post-structure nature of this hybrid system, the BET gas absorption measurement has been carried out. And on the other hand, the nitrogen absorption desorption isotherm curve of the hybrid system has been also calculated and showing that this type of the hybrid systems correspond to the type 7 isotherms in the Bioneer classifications. and showing that it's a typical mesoporous materials. According to the IUPAC classifications, the hysteresis loop belongs to the type H3, which shows a parallel plate split pore structures. Then the pore size distributions of all samples, which calculated from the desorption branch of the nitrogen adsorptions via the Barrett-Helander methods, the pore diameter of the cytosans of this hybrid system were found to be in range of 29 to 11 nanometers respectively, which has further confirms that all samples were in the mesoporous regions, which is the mesoporous region, which is in the 2 to 50 nanometer. The mesoporous structure is important here for the interactive and the absorption sites of the catalyst during the treatment process. For the crystallinity analysis, it shows that the anatase phase is predominant for the hybrid systems. The SRDP of the pure TiO2 and zinc oxide also become significant or visible in the hybrid system, and this confirms that the both of the metal, which is the TiO2 and zinc oxide, were present in the crystalline state of all the samples. The result was also consistent with that what was found in the literatures and suggested that some change occur due to the hydrogen bonding with the chitosan group. In order to study the light sensitivity of this catalyst, the Uvdr spectral analysis has been carried out. And it shows that the band gap found for all the samples were calculated to be in range of 2.75 to 2.49. This result proved that chitosan has lowered the band gap in the gradual trends of the titanium oxide and zinc oxides. And it can conclude that the chitosan induced a band gap narrowing in this system, which result in the use of prepared composite for the photocatalytic removal of the methylene blue dye under the visible irradiations to generate more electron hole pair and give a maximum visible light harvesting. The photocatalytic degradations of the methylene blue was observed for the 60 minutes and 50 minutes as a time interval. Visible spectroscopy was used to measure the rate of decrease in the methylene blue. The result of measurement has shown as the percentage of degradations and the rate of the degradations. The percentage of the photodegradation result, the rate of constant for the photodegradation result for the sample with the different compositions. For this, we have verified the different compositions of the ternary elements, the TiO2, chitosan, and zinc oxides. And it can be seen that the sample with the ratio of 1 to 1, which is the ratio of the TiO2, zinc oxide to the chitosan, have the highest percentage of the photodegradations out of all the samples. The samples show the high rate of constant photodegradations. Based on the results, it shows that there only 10% of the zinc oxide shows the best performance due to the zinc oxide photosensitivity, which influence the degradation of the pollutant itself. And in terms of the effect of the pH, the effect of the pH value of the methylene blue on the percentage of the color removal efficiency has been carried out. At the pH 3, the efficiency of the catalyst reported the lowest percentage, which is at the 96 percentage due to the high acidity stage of the pollutants. Meanwhile, at the pH 5, the percentage of the degradation was recorded 2% higher than the pH 3 due to its lower acidity, which separate the molecule at the much slower rates. For pH 7 and 9, the percentage of degradation were increased up to 75% and 78% respectively. Meanwhile, at the pH 12, the reported of the highest level degradation, which is the 77%, due to the low pH, which more hydrogen ions are available to protonate the amino group of the chitosans. Since chitosan was not cross-linked, it reported a lower absorption at pH 3 for the methylene blue. At the highest pH, the increasing number of negative charge sites on the adsorbent have led to the strong absorptions, and whereby that's why in the result that higher photodegradations has been occur at the higher pH medium. As a conclusion, for this study, we have successfully produced the ternary system of the photocatalyst with a different composition ratios, and it shows that the composition of 1:1 shows a optimized results in terms of the homogeneity, light sensitivity, and crystallinity. And considering the characterization result, the information of the core, its integrity surface appear to have the irregular pores. Band gap narrowing from the 2.9 to 2.6, and it makes sure that this photocatalysis system exhibit a good performance in the visible regions. Chitosans act as a binders to bind the TiO2 and zinc oxides and assist for the absorption of the zinc oxide as the photo dissolution inhibitor. Also, the furthers of the hybrid catalyst inhibit resolve the recycling issues that has been associated to the TiO2 system. In summary, the combination of these three elements provide a facial routes for the treatment of water treatment by maximizing the efficiency which it can be retreated and recycled. The photocatalytic activities of these systems inhibit up to the photo efficiency up to 84 to 90% degradations of methylene blue within 60 minutes of radiations. Thank you. This study has resulted 4 published ISR paper together with 4 winnings medal awards in the exhibitions, international and national levels. Thank you, everyone, and I hope that this sharing session will provide a new insight, especially in water treatment system with the sustainable approach. Thank you for your time and thank you for your attention.
Thank you very much, Dr. Nur Hidayatul Laili Muhammad Kifli, for addressing these exciting topics. Ladies and gentlemen, now we come to Q&A session. Any question from floors? Please, we can take also opportunity for by unmuting your mics to question in line. Okay. We are getting a question from Rida Tazawo. The next step in the discharging this treatment water into the environment. What initiatives will be implemented to ensure the safety of the ecosystem?
Okay, thank you, Dr. Mutalib, and thank you, Dr. Rida, for the questions. So I would like to highlight here that the photocatalysis system is not a discharging method. It's a photo degradation of the process. Means that the pollutant will be degraded into the non-harmful component, just as the carbon dioxide and H2O. So basically, based on our result, that it shows that up to 95 to 99% of the methyl orate compound that we use as the model pollutant compound here has been degraded, completely degraded to this harmful toxic material. Thank you.
Thank you, Dr. Nur Hidayatul Laili, for your presentation and also answer. As there is no more question, we are moving to our next invited speaker and also last invited speaker of today. It's today is the now our last invited speaker of this session is Prof. Dr. Juraida Binte Ahmad, International Islamic University, Malaysia. she will be talking about inkjet printed embedment of PE dot PSS dot SNP as electrons on fabrics. I would like to welcome Prof. Dr. Zuraida binti Ahmad. The stage is yours.
Thank you, Mr. Chairperson. I would like to request for the committee to share the recorded video, and then the question and answer will be answered by my students who are also here, inshallah. Thank you very much. Thank you very much, Chairperson. Assalamualaikum warahmatullahi ta'ala wabarakatuh to the organizing committee as well as the participant of the first international conference on nanotechnology and catalysis. Today we would like to share with all the participants of this book conference on inkjet printed embedment of P.PSS silver nanoparticle as electrodes on fabrics, and this preliminary research was conducted under the theme of our postgraduate student Aisha Ahmad Shahrim, me myself as supervisor, final year project students Nadia Nabila Muhammad Hafiz, supported with Dr. Amelia Wan Azman, Dr. Yosef Fahmi, as well as Dr. Nur Shahida Salihuddin. Our project outline, our presentation outline, we're covering introductions, objective, methodology, findings, as well as conclusions. Metal electrode has been used to treat the pressure ulcer patients. This electrode, however, are hard and rigid, thus causing uncomfortable for the person who is using it. Polymer-based electrode have been noted for promising electrode materials due to their low cost and have been investigated in many biomedical devices, including bioelectrode that will be used to stimulate the blood for preventing and treatment of this pressure ulcer. Conductive polymers such as polyaniline, PAN, polypyrrole, or poly-3,4-ethylene diethylsilophene or P-dot, and composites of these polymers with carbon or inorganic compounds are typically utilized as polymer-based electrode materials. In addition, polymer-based carbon or carbonized polymer are good candidates for electrode materials, and polyacrylonitrile or PAN is one of the most common precursors. In this research, however, we are going to concentrate on the P-dot as a conductive polymer electrode. P-dot itself will not have good conductivity, and it must be doped with something else to increase the conductivity. The structures of polyacetylene, the backbone contains conjugated double bonds. The pi bond between the first and second carbon atom is transferred to the position between the second and third carbon atoms. In turn, the pi bond between the third and fourth carbon travels to the next carbon, and so on. As a result of the electrons in the double bond move along the carbon chain. The PZ orbitals in the chain of the pi bonds overlap continuously, and the electrons in the pi bonds thus move along the carbon skeleton. Thus, conjugated double bonds allow electric flow. However, conjugated bonds do not render polymeric or polymeric material highly conductive. In the P.PSS, the P-dot is a conductive P-type polymer that is not soluble in the polar solvents such as water. Therefore, it is doped with PSS, which is an ionic conductor, to provide a stable, easy to process deep blue water-based P-dot PSS dispersion. The PSS in the complex functions as a counter ion for cationic conductive P-dot. Although the additions of the PSS bring an enhanced processability, this comes at the expense of a decreased electrical conductivity. So in this model, oligomer P dot segments are tightly by ion interactions bond attached to PSS chain of much higher molecular weight, and that calls out to form a tertiary structures. So the high conductivity P dot PSS dispersion can then be attributed to set arrangement of the P dot chain within a large tangled structures of loosely cross-linked, highly water-soluble particles. So the P dot PSS has a tertiary structure with a diameter of several tens nanometer, where hydrophobic P dot molecules aggregate to form a physical cross-link between the PSS chain in water. Added organic co-solvent in ink formulation may bring a screening effect between the positively charged P dot chains and negatively charged PSS chain, and then reducing the column interaction between them, which causes a phase separation between P dot and PSS. Nevertheless, this co-solvent do not possess antimicrobial properties to prevent pressure ulcer from bedridden or limited mobility patient. So a component, a material need to be added so they have the advantage of having antimicrobial properties. Not just as antimicrobial agents, this SMP can be another strategy to improve the electrical conductivity of a conjugated polymer through the incorporations of this nanoparticle into the conducting polymer. SMP exhibit highest conductivity among the highest transition metal. It acts as an antimicrobial agent, that's what we mentioned earlier, making it suitable for the biomedical applications. Since electrode will be placed underneath the patient's skin, the P dot PSS able to absorb the moisture from the sweat. Meanwhile, SMP able to prohibit the microbial growth, and it's good for preventing pressure ulcer. So the typical particle shapes of the SMP is in spherical and will able to provide the inhibition of the microorganisms and bacteria. So the possible bonding between the P dot PSS and SMP has been established where the SMP attached to P dot chains and balancing the counter ion from PSS. Yet to be used as in the spherical shapes of the SMP might dogging the print head and cartridge nozzle to the agglomerations of particles, even though the SMP is claimed to be homogeneously mixed with P dot PSS. So by employing appropriate preparation method of the SMP like sonications and applying filtration before injecting the ink into the cartridge should be minimizing the risk of agglomerations of the SMP. Therefore, a uniform film based on P dot PSS dot SMP will be developed. So a uniform film based on the P dot PSS dot SMP will be developed, and this is what our research all about. Objective of the research. So our objective of the research is to investigate the appropriate or the optimum amount formulations of P dot PSS SMP with the incorporations of cool solvent like dimethyl sulfur oxide, ethylene glycol, ethanol, isopropyl alcohol, and the ionized water to be used during printing on cotton fabric. And we are to the objective is to evaluate or to assess the physical, morphological, and functional properties of PEDOT-PSS SNP inkjet printed embedded on the fabric. So the methodology. So we talk about the formulations. So the content of each of co-solvent, for example, like the MSO, ethanol, is obtained from the literature by choosing the one of the researchers reported that shows the optimum property of like high conductivity that we are targeting of. So SMP content is chosen based on our previous work by taking the ratio of 1 to the ratio of 2 for P dot to PSS and as well as SMP respectively. So the content of IPA and the ionized water is taken from the study reported by Soleimani Jojani, the research who are having made their report, research report on research article in 2018. So the composite ink prepared by the ultrasonic dispersion technique for depositing using drop-on-demand inkjet printing. So this is basically the physical properties of the inkjet printing to the fabric materials. This is 1 layer, 3 layers, 5 layers, 10 layers, 15 layers of the printing. So you might see that this is 10 to 15 layers with different materials. So we can see this is ink number 3, ink 2, and this one in green in color is ink 1. So the higher number of pretty layers, we can see that the darker color of the ink. It is expected that the larger number of printing layers, the lower the resistivity. When the resistivity is lower, of course, the higher the conductivity. So the pattern shows that the uniformity of the PEDOT-PSS film despite of different in formulations. We would like to see the electrical properties of our inkjet printing to the material. So as mentioned earlier, we have inkjet 1 formulation for ink 1, for ink 2, and as well as ink 3. And we have a control here for the fabrics only. So basically this is all the results obtained. So in 1, it is in green in color, blue is for ink 2, and purple is for ink 3. So we can see that at 15 layers, the resistivity of the what we call it inkjet 2 and ink 2 and ink 3 increases in comparison with ink 1 because of the limits of charge carrier mobility between the dried particles in an inkjet printed film, causing by the interactions between the PEDOT-PSS, silver nanoparticle, and as well as co-solvent. So ink 3, on the other hand, reduces resistivity when printing up to 10 layers due to the phase separations between PEDOT and PSS causes by the reductions of Coulombic interactions between them, since screening effect between positively charged PEDOT change and negatively charged PSS change occurs when adding ethanol and EG in the into formulations. All right, so we might see here. So the optimal printing layer in this work is suggested at 10 layers, since the trend is in agreement with the hypothesis, which the additions of co-solvent in PEDOT-PSS dope SMP provides lower resistivity, hence it will increase or make it conductivity higher. For the morphological properties, the surface morphology of the fabric and PEDOT-PSS fabric printed with 15 layers were examined and displayed in this figure. It was revealed that the PEDOT-PSS ink that is ink 1, was well dispersed on the threads of the fabrics with the presence of coagulations of PSS at certain area. This implied good interactions between the cotton fibers and PSS, thus promising for developing conductive fabric. The observation was also corroborated with the low resistivity of the sample, since the presence of few numbers of SMP particles and agglomerated particles. So the surface of I3 in 3-base fabric presented SMP particles and free from agglomerations of any particles. So this indicated the improvement in homogeneity of in 3 was obtained with the additions of the ethanol and EG in the ink formulation compared to I3. So the results suggested the ink based on PSS has been well embedded on the fabric. The functional properties result can be observed in this graph. All right, the functional groups existed in the cotton fabric, and the in 3-base fabric presented here. So the prominent peaks of the cotton fabrics were observed at 3322, 2904, 1630, and as well as 1025 centimeter at the wavelength of centimeter to the power of -1, which attributed to the stretching of OH, stretching of CH, OH bending, and as well as CO stretching respectively. So similar peaks were also displayed when embedding in 3 on the fabric via inkjet printing method shown in the articles, in our articles. It is noticeable that there was this displacement of peaks due to the hydrogen bonding interactions between the cotton fiber and the PSS silver nanoparticle base ink. The intensity of the peaks was also decreasing, that is associated with the existence of some other components present in the sample. As a result, the findings confirm the successful introductions of co-solvent, for example, like the MSO, ethanol, and AG as conductive enhancers to the PSS SMP via inkjet printing. So, and then the mechanism for PSS conductivity enhancement. So let us go through it, and it is very nice to see the mechanisms. We can see that with the additions of co-solvent in PSS and SMP, it will screens the ionic interactions between what? Between film and PSS ion by creating hydrogen bonding with PSS. And then this proceeding to phase separations between film and PSS and linearly oriented chains, leading to the conductivity enhancement of PSS. So basically that is our preliminary results. So the conclusions from our research, we can see that in formulation based on PSS doped with SMP and blended with the MSO, EG, and ethanol for inkjet printing on the cotton fabric has shows successful printing. So the additions of the co-solvent as the conductivity enhancer has been confirmed with the decreasing value of resistivity about factor of 1.5 to 10 printing layers. So the morphological properties of the PSS based fabric reveal a well disbursement of the ink supported with the successful of adhesions on the cotton fiber evidenced by the FTIR spectra. So the mechanisms of the conductivity enhancement for PSS also proposed based on the finding where the screening effect between the p-dot chain, SMP, and the co-solvent, making the PSS chain separated and rearrange the orientations of the conductive polymer. So of course, this is a preliminary work. There are further work need to be conducted to achieve the main objective of the whole project, which is to develop a medical electrode based on P.PSS, SMP, and there are some other characterizations like Raman, UVVs, EFN, and XPS need to be done. By that, if you have further questions regarding it, you can ask after this recorded video. Thank you very much and Jazakallah khair. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Thank you all.
Okay, thank you, Prof. Dr. Nuraida Binte Ahmad, for your informative and exciting topics. Now we come at the QA session. Any question from floor? Okay, Prof, I would like to take opportunity to ask a question. Yeah, now inject ink is available, printer ink in market, and compared to the market inks and you develop new ink, what will be the price difference? And another, what is your stage of research have about planning to marketing immediately, or what is the condition?
Thank you, Mr. Chairman. Actually, I would like my student to ask, but before she to answer. But before she answers, I just would like to highlight that we are doing. There are many inkjet printing, but this is very special because of the formulations. Because we tried many formulations, and because of the sometimes, if it is not a good formulation, it will stuck inside that inkjet printing and it causes trouble to the inkjet printing. Then we cannot print it. So currently we are trying to find a good formulations, not to just inject it to the fabrics, but as well as will conduct a good electric conductivity, so that it can be a bag that can be used for pressure ulcer patients in the hospital. So am I answering your question?
Okay, thank you, Prof. Okay, I understand.
I'm sorry, I cannot open my camera. Okay.
Okay, no problem. Our next question from Dr. Rida: the ink transmission or opacity on the substrate, does it provide the desirable properties for the study? Yes, please.
Okay, thank you for the questions, Dr. Rida. Because currently we are too much focusing on the functionality, meaning that we can be used inside the inkjet printing, one thing. And the other thing, we are really want to use it for pressure ulcer, as I mentioned earlier. So we are not concentrating on the transmissions or opacity. We are just concentrating on two factors only currently, that it can be injected, and then the resistivity is very, very low, so that the conductivity are going to be, the electrical conductivity are going to be high. So we are not concerning either it's desirable or not. We are not yet in our study plan or research plan. So am I answering your question, Dr. Rida?
Okay. All right. Okay, Prof. It's okay for your answer. As no more question, so we are going to end of our session. Before closing, we have some announcement. Now I am very honored to announce the best presenter for session Biomaterial Polymers 2 is going to Miss Anusha Wi Ashuhan. Congratulations to Miss Anusha Wi Ashuhan as a best presenter of this session. Now we reach at the end of this session. Thank you for your participation. On behalf of MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form as given by session moderator in the pull box. You are invited to join the rest of the events. Our next session will be keynote session 3 at 9 a.m. tomorrow, inshallah. Hope to see you again. Thank you. Thank you for your participation.
Thank you very much.
Thank you, Dr. Mutalib.
Thank you, Prof, for your participation and cooperation.
Thank you so much, everyone.